You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. Although the majority of AC offline converters and switching converters that run from hazardous voltage include galvanic isolation for safety, there are many applications where non-isolated circuits can be used, where mechanical isolation protects the user and service personnel from contact with the hazardous voltages, or for where both input and output voltages are on the primary side of isolated converters. The buck regulator and buck boost regulators are often more efficient, use less PCB area, and cost less to implement than the flyback regulators. Flyback regulators, without a doubt, are the least expensive option for isolated circuits and can, of course, be non-isolated as well. However, even at power levels of 5 watts and below, the flyback still requires a coupled inductor, also called a flyback transformer, and includes varying turns ratios depending on input voltage, output voltage, the range of output current, and even the switching frequency. Worth Electronic offers several families of the off-the-shelf flyback transformers, but when the circuit does not require an isolation, the buck and buck boost become the more attractive options because they can use a much wider selection of off-the-shelf power inductors that can be more affordable. Now, there are 3 common off-the-shelf power inductor topologies for energy storage in offline circuits for either universal AC input, that is 85 to 265 VAC, or the European line voltage, which is 195 to 265 VAC, where the peak DC voltage after rectification approaches 400 volts DC. Now, unlike the inductors used for filtering, the energy storing inductors in each of these 3 circuits endure differential voltages equal to or even sometimes exceeding the peak input voltage. Worth Electronic offers 3 families for a total of 6 series of power inductors in shielded and unshielded surface mount technologies, along with unshielded through-hole technology that's been designed specifically to operate safely in the presence of differential voltages well up to 400 VDC. The first figure attached in this podcast shows a standard buck converter with a half-wave rectifier. It allows the ground reference to be the neutral of the AC input line. The output voltage, or V out, and the input voltage share the same ground reference as they do in low voltage, non-isolated DC to DC converters, making this circuit ideal for generating the operating voltages for ICs that are referenced to ground on the primary side of the AC to DC regulators, both analog, such as power supply controllers and gate drivers, and also microcontrollers or interface circuits. The main disadvantage of a standard buck regulator that it's operating in the 400 VDC is that the control switch is floating. This is also known as in the high side. Silicone die area and also cost force the use of N-channel MOSFET switches. So to control the gate, the control IC must either use high voltage silicone or they have to incorporate a level shifting circuit. Several well-known power management IC manufacturers now offer a combined control positive HV MOSFET device, and it greatly simplifies the control and level shifting to make this topology practical. To the right of that image in Figure 1 attached in the podcast, we see an alternate buck topology where the control switch is ground referenced, or also known as in the low side. In general, this topology is a lot easier to implement because of the ease of driving a ground referenced and MOSFET switch. The same combined control positive high voltage MOSFET ICs can be used, with some actually capable of operating directly from the 400 VDC input, while others require a low voltage supply for their control sections, generally ranging from 12 to 24 VDC, and is generated with a discrete linear regulator. This topology is a negative buck when it's used to step a negative input voltage down to a negative voltage of lower absolute value, but when connected to a positive input voltage, it's called a floating buck, low side buck, or input referenced buck. This is owing to the fact that the output voltage is controlled with respect to the positive input rail. The two main uses for this type of topology include being current sources for LED drivers and also as voltage regulators for the low power systems where no other circuitry requires a reference to the ground on the primary side. A small AC mains powered communications device is a good example of this, where the microcontroller and an isolated interface circuit would both be powered from the voltage labeled VLED. Our final image to the far right of Figure 1 shows a buck-boost regulator developing a negative output voltage referenced to the negative input rail. Some applications used in this topology include negative voltages for powering op-amps and also for controlling triacs that switch AC mains in and out of circuits on the primary. Two details that require attention in buck-boost circuits are the additional voltage stress across the MOSFET, output diode, and the inductor, and also the discontinuous high RMS seen by the output capacitor is similar to that of the output in a flyback converter. Safety standards such as IEC 60950 are relatively clear in stating the distance through air and distance along a surface, between isolated primary and secondary circuits, between AC mains line and neutral, and between those points and protective earth. Most standards are more difficult to interpret for other voltages, like the positive and negative outputs of a diode rectifier that form the input voltage to AC offline circuits. The isolation category for voltage nodes within non-isolated circuits is functional isolation. This means that the distance between nodes is whatever is needed for the circuits to function properly. One common way to establish guidelines for PCB layout and also to evaluate the physical design of a power inductor is to review the transient voltage tests applied to the equipment being designed. For example, in IEC 60950, equipment operating from voltages up to 300 VAC RMS is tested with 1500 VDC pulses if it's class 1 with a protective earth ground, or 2500 VDC if it's class 2 without protective earth. 300 VAC RMS includes the majority of AC and HVDC applications where low power, non-isolated bucks and buck boosts are used. Arcing across PCBs can be avoided in most classes of humidity and pollution with a clearance of 1 millimeter per 1600 VDC. Now, as recommended by Underwriters Laboratories, many power supply designs use the Class 2 ratings for creepage and clearance, even if they are Class 1. This gives them an added margin of safety. To avoid arcing during the transient voltage tests of 2500 VDC, a distance between pads and terminals of the inductor used should be approximately 1.6 millimeters or more. In each of the three topologies that we stated earlier, one side of the inductor is held to a fixed voltage, and the other side is commonly referred to as the switching node because its voltage slews back and forth from 0 to voltage in for the buck and floating buck, and from 0 to voltage in plus voltage out for the buck boost. Maintaining that distance of 1.6 millimeters from the switching node to the other nodes in the circuit is beneficial. It not only prevents arcing during transient tests, but it also reduces capacitive coupling and is helpful in reducing common mode noise if any traces or planes with earth ground are present on the PCB. In our next attached figure, number 2, we see the smallest member of each of the 3 families of HV rated power inductors, and each shows more than enough clearance between the electrical connections to prevent arcing at 2500 VDC. The magnetic cores of inductors, and don't forget the transformers, are considered to be conductive parts as per IEC 60950, and so their level of insulation is functional. It's often common practice to use the same families of through-hole and surface mount power inductors as both the energy storage elements in low-voltage DC-to-DC applications and for input or output filtering in offline applications. But there's one important factor in both of these applications that is often overlooked. It's the voltage rating of the inductors. In fact, the vast majority of power inductors actually lack voltage ratings in their data sheets. Good quality manufacturers can provide this information if you request it, or they can provide information on the thickness of the varnish used or other details of mechanical construction. But by the time that you calculate the voltage that a given inductor can withstand, it's completely out of step with today's fast-paced design cycles. In a rush to complete design work on time, it could be tempting to select a standard power inductor, but unfortunate results could occur when using these parts in high voltage applications, such as breakdown of the insulating varnish, short circuits between adjacent windings. In short, failure of a component that's normally the most robust part of a switching converter. A shorted inductor, especially one that could short AC line and neutral together during part of the switching cycle, presents a genuine safety hazard to both operators and service personnel. If electric shock, injury, or even death occurred as a result, the equipment manufacturer can be held liable. The following families of inductors are guaranteed to operate properly with up to 400 VDC according to Worth Electronic ISO standard 1516. Those series included are WE-PD HV, WE-PD2 HV, and the WE-TI HV. This guarantee remains valid even after 3 reflow processes, making Worth Electronic the first manufacturer in the world to provide such a robust guarantee. Operating in CCM, where inductor current stays above 0 over the complete switching cycle, has the advantage of lower RMS currents, not only in the inductor, but also in every other powertrain component as well. Lower RMS currents means less power dissipation, lower operating temperatures, and lower EMI. The major disadvantage, though, is the high inductance needed, which in turn leads to physically larger inductors and sometimes to values that don't exist in catalog products. These design examples use the Viper 16L IC from ST Microelectronics, and they meet these conditions including buck and floating buck and buck boost topologies with input voltage of 360 to 400 volts, output voltage of 12 currents, maximum output current of 200 milliamps, continuous, a switching frequency of 60 kilohertz, and delivering 2.4 watts. Magnetics form the heart of any switching converter. Regardless of topology, the most common way of selecting the required inductance in CCM is to specify a ripple current through the inductor as a percentage of the maximum average inductor current. Setting the inductor ripple current equal to 20 to 40% of the maximum average inductor current represents a good compromise, tested and confirmed by the design of countless switching converters, and gives a balance between size and efficiency and noise. The smaller ripple leads to lower RMS currents and lower EMI. For buck converters, maximum average inductor current equals the maximum output current, with the floating buck sharing the exact same design equations with the standard buck. In buck boost converters, average inductor current is a function of duty cycle and output current. Attached in Figure 2 are the first order equations for a ripple ratio of 30%. The next highest E12 value is 3.3 millihenry, designated L1. Once this value has been selected, then the actual inductor ripple current and the peak inductor current can be calculated. You can find this calculation in Figure 3 attached in this podcast. With inductance, average current and peak current, all calculated actual inductors, can be selected from the Worth Electronic ISOs catalog. The example we have comes from the WPD-HV product family. It is a 3.3 millihenry shielded device specially designed for 400 VDC operation with an RMS current rating of 0.37 amps and a peak current rating of 0.52 amps. This part uses surface mount technology, and it's best suited to two-sided PCBs that are already incorporating other surface mount circuitry. Lower cost applications often use single-sided PCBs and purely through-hole technology. But in this case, the principal disadvantage of CCM operation is pretty obvious. There's no 3.3 millihenry high voltage rated through-hole parts available. Our previous example can still be operated in CCM with lower values of inductance. The 768772 WTI high voltage family from Worth Electronic offers a 2.2 millihenry part, and it's rated for 0.32 amps average and also 0.32 amps peak that will work perfectly, albeit with higher peak-to-peak ripple current. The actual boundary where CCM operation is no longer possible occurs when the peak-to-peak ripple current equals exactly twice the average inductor current. A combination of switching frequency jitter and the input voltage ripple make it difficult to capture the inductor current touching zero. This means that the circuit moves back and forth across the DCM-CCM boundary from cycle to cycle. The point where the inductor current just reaches zero at the end of each switching cycle is often called the boundary conduction, or the BCM, and it can be defined mathematically. You can find this equation attached as Figure 4 in this podcast. These equations show the inductance values above what the converters would operate in CCM when delivering their maximum rated load currents. In non-synchronous converters, there will always be a threshold of output current below what the converter will transition from CCM to DCM, regardless of how large the inductance is. There's no harm in DCM. In fact, for high voltage non-isolated applications, it's actually more common to operate in DCM under the full range load. In CCM converters, once the actual inductance has been selected, the equations can be rewritten to show the threshold for boundary conduction as a function of load current. In DCM, the current in the energy storage inductor falls to zero before the end of every switching cycle, and in order to operate in DCM, the switching converter must either use a diode as an uncontrolled switch or actively control the synchronous MOSFET to prevent current from flowing backwards. For cost purposes, it's far more common to use a diode, and for operating voltages above 200 VDC, the preferred technology is the ultra-fast PN rectifier. The principal advantage of DCM is that the inductance must be lower to ensure that the converter stays in DCM even at its highest load. Lower inductance translates to a smaller core, which means smaller, low-cost inductors. A second advantage of DCM is the reduced switching losses in the control FET, since the current in the inductor is always zero when it turns on. Design examples for a buck or floating buck and for a buck-boost regulator operating in DCM are shown in Attachment 5 for the same set of operating conditions as the CCM, which we discussed earlier. The same equations used for identifying the boundary between DCM operating and CCM operation are used to select inductance for the DCM case. The only difference is that now they set a maximum permissible inductance. In theory, any value below L max, or maximum inductance, will work, but because inductance and peak current are inversely proportional in practice, it is best to select the next lowest standard value in order to prevent peak current from reaching excessive values. A standard E12 value of 470 microhenry will work for both designs, and in order to select an actual device from a catalog, the peak currents for each topology must be calculated. Peak current and peak-to-peak ripple current are equal in DCM, and to calculate this value, you need to calculate the duty cycle first. With an actual inductor value selected, the amount of energy transferred from input to output during each switching cycle is known, and the duty cycle of the control FET in each topology can be calculated. Based on the limits for inductance and peak current, an actual inductor can then be selected. The 768-771-4471 from the WePD-HV product family is a 470 microhenry inductor with a saturation current limit of 0.8 amps. This is a surface mount part that includes magnetic shielding for low EMI and measures 10 by 10 by 6 millimeters tall. Most important of all, the 768-771 family features design and post-production testing to ensure that its parts function correctly with differential voltages of up to 400 VDC. Now, such a part would be a good choice for dual-sided PCBs where an HV non-isolated buck accompanies other surface mount circuitry. But for simpler applications where the PCB has a single layer and less expensive through-hole parts are used for capacitors, diode, MOSFET, and resistors, then a better choice would be the 768-772-471 from the WeTI-HV product family. This is a through-hole device, also 470 microhenries, and with a saturation current rating of 0.9 amps. All three product series of inductors from Worth Electronic, the WePD-HV, WePD2HV, and the WeTI-HV, are guaranteed to operate properly with up to 400 VDC, even after 3 reflow processes. To find more information and to order your samples of these high current inductor series, visit Worth Electronic online at www.we-online.com. You can also download this application note by clicking the link available in this podcast. You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast.